cases. Now, we go to the surface roughness comparisons. We have basically 8 categories, cavities. The second page. Again, we look at the 3 regions. And for the welded seam, we look at the surface roughness. Obviously, that makes not much difference because welding makes all the grain large enough or very smooth. Same thing happens to heat effector zone. There's slight difference, but mostly heat effector zones also gets changed by the electron beam actions. So we have to look at the normal areas, which means pretty significant differences among these many cavities. So we summarize the next table here shows these 8 categories cavities. We plot the surface roughness in RZ versus their maximum EACC. From this table, it seems to be that once you reach a certain level of the surface roughness, you don't gain much about the cavity gradient. So that's something very surprising. We thought going the best surface roughness will get you an indefinite high field until a theoretical limit. So now that we said surface roughness or surface feature is secondary role, so what's the first role? That's what Alexander Romanenko is doing. We got this cavity tested, and the geometric defect shows no quench. The quench actually happened at the other locations, so he's cutting this cavity out to do surface analysis. I'm not sure if he's going to show these results tomorrow. Maybe he will. So that's a work in progress. Now, how does this relate to the thin film? I think for the bulk niobium, that's not the case. But for the thin film, it's absolutely important because we know from this morning that the top layer is very vulnerable to magnetic field enhancement. If the field penetrates into the substrate material, you lose all the benefit of the films. So you have to absolutely push the surface roughness or the surface topology to the best you can. That's very different from the bulk niobium. So this picture shows the 3 cavity features in linear scale. And next I want to try to introduce this brief describing Fermilab's effort in terms of pushing the limit of the surface preparation. We have a tumble machine, we have EP system, and they also team up with a local company to do the chemical and mechanical polishing. So the BCP, the cavity, they have rough surface in the equator region. After tumble, gets very smoothed. And the EP, you get almost a very perfect film. That's our starting point for the chemical mechanical polishing. And of course, the work is still in progress. We don't have the results yet, other than I'm showing you the on a small sample with the starting point, which is the cavity, which niobium sample has a 3 micron surface roughness. After chemical mechanical polishing, it went to 35 nanometer. And that's still not the best they can get. I was told they can almost get to atomic flat surface. So here's the conclusions. That the cavity replica can be a great tool to identify the quench site for the bulk niobium cavities. And those defects can be classified as geometric imperfections or intrinsic to the material. And among those things, we say that the geometric imperfections only the secondary role. The existing process technique can reduce the magnetic field enhancement if the intrinsic material is not present. And the material study is a must to understand what happened to those quench locations. So perfect substrate preparation, of course, still remains a challenge for the thin film SRF. And I wanted to say one word. Fermilab is very interested in high Q operations for Project X. And the time scale probably within 5 to 10 years, if we can find some thin film application for highest Q available for CW LINAC, people will take it. That's all. Thanks.